Hi, today we're going to talk about brain, about cognition, how to measure brain performance, how to measure cognition. You can see, like in the story about the blind researchers and the elephant, that there are many ways to approach this task. And wherever you look, and from whatever perspective you choose to study this issue, you will find different answers and different interpretations. So the brain is flesh. It's mass. You can weigh it. You can see infarcts. In the living tissue, you need to modulate that, of course. You can see in SPECT, MRIs, the size of the infarct, like the image on the left side. The brain is also chemistry. If we want to learn about mechanisms of communication in the brain, we need to look at the synaptic cleft, where different chemicals help to send different signals of information from one neuron to the next. We can also look at the brain as networks, signaling with electricity signals. We can use these signals to learn about innate or acquired knowledge in the brain. The brain is, of course, responsible for many functions. Cognition is only one of many functions the brain is responsible for. The brain is, of course, responsible for motor functions, for autonomic functions, for hormonal functions. We will concentrate now on cognition. Cognition is actually a man-made theory, configuration of different functions in the brain. Cognition is responsible for understanding and reacting according to something we understood. So here we can see the different cognitive elements, the cognitive functions that we are monitoring in Aviv Scientific. These elements are relevant for elderly population, healthy elderly population. We know from vast amount of research that these cognitive elements go down, decrease as we age. The first element we will talk about is attention. Attention is like a spotlight. You can see here a spotlight. Whatever is in the diameter of the spotlight will be attended to. Whatever is outside of the diameter will not be attended to. This diameter, this spotlight, has many attributes. It can be with strong light. It can be divided into different objects. Let's see an example. Take a look at this face over here. Try to find the hidden camel. So it's not that easy to find the camel. You can see here many other animals, other big animals. You can see here a whale. You can see here a dolphin. The camel is actually hidden on the right cheek. Take a look at the right cheek. There's a small golden camel hidden over there. Now, why do we find it hard to attend to this camel? Our attention is calibrated according to the big animals. Therefore, they are distractions. And when there are many distractions, we find it hard to attend to the target we are looking for. Take a look at a second example. On the right, you can see a matrix with many letters. Try to find the mismatching letter. So in the fourth row, there's a B hidden there. Now, why is it hard to find the B? It's hard because, once again, the noise to target ratio in this example is benefiting the noise. There are much more distractors, and there's only one single target. Our attention is very distracted by noise. It's harder to find the target as the noise grows. So let's look on the example at the left. This paradigm is called the flanker paradigm. We need to press the arrow that corresponds to the central arrow on the screen. When the target and the distractors are corresponding to each other, we do it fairly easily. It's fairly easy on our attention. But when there is a conflict between the target and the distractors, it's harder for our attention to focus on the target, and it takes us more time to do the action. Information processing speed is another element of cognition that is relevant for older population. Information processing speed refers to the way we optimize accuracy and reaction time. When we have to solve a simple task, for example, a task like this one, usually it will take most of us a short period of time, and we will do it with high accuracy. But if we have to solve a difficult problem, for instance, in this task, we need to count how many triangles are hidden here. This will take some people a longer time. Some people will solve this fairly quickly with high accuracy of rates. We differ in the way we optimize accuracy with response time. By the way, this is the answer to this task. Working memory is a cognitive platform where we store information for short periods of time for further processing and manipulation. A way to assess working memory is in this example. We can see here a sequence of blocks lighting up on the screen. The sequence will grow longer and longer. And after each sequence on display, the subject will have to retrieve by pressing on the right order of blocks. When the sequence exceeds the subject's span, we have the visual working memory span of the subject. Another element of cognition is encoding. Encoding refers to the way we register information before it's consolidated into memory. Encoding is the way we organize, register the data so it will be easy for memory to do the consolidation process. Take a look at this list over here. This is a list of 16 words. If I ask a subject to try and memorize these words, he will look at the words, and then when I tell him, he will recall as many words as he can. But when we are measuring encoding, we are not actually interested in the number of words he recalls. We are more interested to see whether he understood that there are categories in these lists. In this list, we can see that there is a category of sport, there is a category of food, etc., etc. Encoding is the process of organizing the data into categories or into other elements of organization that will make memory more simple. Retention is our capability to hold information in our memory for short periods of time, longer than the time they are activated in the working memory. We can measure retention by simple paradigms. For instance, you can see here in this slide that we will show you 8 different objects on the screen, and then after a delay we will ask you to reply, to recall, to retrieve the most fitting object according to what was shown before. Response inhibition. Response inhibition is the gate for higher order thinking processes. On the left, we can see Phineas Gage. Phineas Gage was a coal miner who lived in the United States of America back in the 19th century. He was hit very hard in his skull. You can see, actually, this is the real skull of Phineas Gage. He was hit by a stick that went into his left orbit and went out of his frontal lobe. He survived this blow to his brain, but after that, Gage was no longer Gage. He was very much disinhibited. He was very impulsive. Some said he was acting like an animal. He had no control on his drives, on his urges. Since Phineas Gage, we know that response inhibition, which is usually located in the frontal lobe, is the gate to higher order processes. And I will give an example. If we see a banana on the street, we will look at it and we will think whether we want to eat it or not. What is this? Is this a banana? Is this something else? What else can we do with a banana? This is much different than an ape who will see a banana and he will have no response inhibition and he will just go to the banana, pick it up, and eat it. So our ability to inhibit our responses enables us to think in a higher order. This is an example of how we measure response inhibition. This is the very famous Stroop paradigm. In this paradigm, we are asking the subject to choose the color of the font in which the word is written. So the right answer in this trial is green. But in order to press on the right color, the subject first needs to inhibit his automatic response to the word in the display. He needs to inhibit his response to the red and act according to the green. This is how we measure response inhibition. Cognitive flexibility is our ability to change thinking modes, our ability to switch from one thinking mode to the other. In real life, this is very important because if we are doing something and we are stuck, we need to have the flexibility, the cognitive flexibility to switch to another modus operandi and do something else. In the clinic, we measure cognitive flexibility with the trail-making test, for instance. In this test, the subjects need to draw a line switching between numbers and letters. In order to do that, he needs to have the flexibility switching from one set to the other, back and forth. Here we can see another example of a cognitive flexibility paradigm. In this paradigm, there are two sets of action. If the leaves are green, the subject needs to press the arrow according to the orientation of the leaf. When the leaves are yellow, the subject needs to press the arrow that corresponds to the direction of movement of the leaves. As you can see, there is an interchange between the colors. Sometimes it's green, sometimes it's yellow. The subject needs to react accordingly and switch his modes of operation. Rates of compliance is something that we also need to take into account. It could be a very good task, but if it's hard, if it's complex, if it will bore the subject, if the subject will show low rates of compliance to the task, then the task is not relevant. The task should also give us a large scope of data. We like tasks that give us a big matrix of data. So in the end, the task should have a high cost effectiveness. It should be short, not too complex, with high rates of compliance and giving us a big scope of data. When we're talking about feasibility of the task, we should also make sure that there is no floor effects or ceiling effects in the task, that the task is sensitive also in the high ends of performance. The stability of the task is very important for its reliability. We need to make sure that the measures are stable and that they are not influenced by things in the environment. If the subject performs in one way on a single day, but performs completely different on another day, then we don't have a good test. We need to make sure that the measures are not influenced by things like hunger, mood, pharmacology, the date of the year, etc., etc. We measure the test-retest using a large matrix of correlations. We administer the task a first time, we administer the task to the subject a second time, and then we calculate the correlation of the measures. We choose only the measures who have a high test-retest rate. After making sure that we have stable measures, we still need to make sure that they are sensitive to the clinical manipulation. In our firm, the clinical manipulation is the hyperbaric oxygen. Not all of the measures will react in a sensitive way. Not all of the measures will show sensitivity to the manipulation. In the end, we will choose only the stable measures who also change before and after the hyperbaric oxygen. After we have all the relevant measures, those which are both stable and sensitive to the clinical manipulation, we organize them in clusters. These clusters will later be the indices, the cognitive indices that we present to the subject for him to monitor his cognitive progression. Here is an example of one of our tests, one of the tests we are using at Aviv. It's called the NeuroTracks test. We can see that in this test, the different measures are already organized into cognitive indices. We have a memory index, we have a verbal function index, we have an attention index. We can see in this graph, in blue is the measure, the index, before the hyperbaric oxygen therapy, and in red we can see the same index after the hyperbaric oxygen therapy. You can see that all of the measures show a progression in the ability. Thank you very much for joining me. If you have any more questions, I am here to assist.